December 1942. Building 4, Chrysler Tank Arsenal, Warren, Michigan. The production floor stretched a quarter-mile, lined with M4 Sherman hulls at various stages of completion. Riveting guns hammered in staccato bursts. Arc welders threw blue-white flashes across the concrete. The air tasted of hot metal and cutting oil. On average, each tank required 18 days to move from raw steel to a finished combat vehicle. 18 days that Allied commanders in North Africa didn't have. Field Marshal Erwin Rommel's Africa Corps had devastated American armor at Kasserine Pass 2 months earlier, destroying 183 tanks in 4 days. The replacement rate wasn't keeping pace with combat losses. Production had to accelerate, but every engineer at Chrysler, Ford, and General Motors insisted the current timeline was optimal. The assembly process had been refined through 2 years of continuous improvement. 18 days represented the physical limit of what was achievable. What none of them knew, what the production managers and military liaisons and efficiency experts couldn't have predicted, was that a 34-year-old tool and die maker named Charles Sorensen was about to propose a modification so counterintuitive, so apparently reckless, that his immediate supervisor would refuse to forward it up the chain of command. Sorensen wasn't an engineer. He hadn't attended college. He'd learned metalworking in a Detroit automotive shop, spent 15 years cutting dies for Ford's Model A production, and transferred to tank manufacturing when Chrysler converted its operations for military production in 1940. But Sorensen had noticed something the engineers missed, and his observation would cut tank production time from 18 days to 38 hours. The story begins not with Sorensen, but with the tank he was trying to improve. The M4 Sherman medium tank, standardized for production in September 1941, represented America's answer to German armored superiority. It weighed 30 tons fully loaded, mounted a 75mm main gun, carried a 5-man crew, and could sustain 25 miles per hour cross-country. By late 1942, 11 factories across the United States were manufacturing Shermans at a combined rate of roughly 1,000 per month. This was insufficient. The War Department had calculated that defeating Germany required deploying 16 armored divisions to Europe by mid-1944, each division fielding 300 tanks, plus replacement vehicles to cover combat losses, which intelligence estimates suggested would run at 30% per month during active operations. The mathematics was brutal. Maintaining 16 divisions in combat required producing approximately 2,500 tanks monthly, every month, from January 1943 through May 1945. Current production rates achieved less than half that figure. The bottleneck wasn't raw materials. American steel production in 1942 exceeded 80 million tons annually, more than Germany and Japan combined. The limitation was assembly time. Building a Sherman required approximately 8,000 individual operations. Cutting armor plate, drilling mounting holes, welding seams, installing transmission components, mounting the turret ring, calibrating the gun traverse mechanism, wiring electrical systems, painting, and testing. Each step consumed hours. Some required specialized equipment that couldn't be duplicated. Others demanded craftsmen with skills that took months to develop. The War Production Board had authorized expansion of existing facilities and construction of new arsenals, but training workers and installing machinery took time measured in quarters and years, while tank losses in combat were measured in hours and days. Military planners had studied Soviet production methods. The T-34, Russia's medium tank, required only 3,000 man-hours to manufacture compared to the Sherman's 10,000. But Soviet techniques achieved speed through simplification that compromised reliability. T-34 transmissions failed after 200 miles on average. Gun sights were crude. Interior finishing was non-existent. American doctrine emphasized mechanical reliability and crew survivability, standards that added complexity Soviet factories ignored. The German approach offered no lessons either. Panzer production was meticulous, precise, and catastrophically slow. A single Tiger I required 300,000 man-hours to build. Germany manufactured only 1,350 Tigers during the entire war. American factories would eventually produce 49,234 Shermans. Quality versus quantity represented a strategic choice, not a technical limitation. America chose quantity, but current production methods weren't delivering numbers fast enough. Charles Sorensen understood none of this strategic context. He showed up at the Chrysler Arsenal each morning at 6 a.m., clocked in, collected his tool assignments from the foreman, and spent 8 hours cutting, grinding, and fitting components. His workstation sat adjacent to the hull welding section, where armor plates were joined into the Sherman's basic structure. The welding process fascinated him, not the welding itself, which he didn't perform, but the preparation. Before welders could join two plates, fitters had to align them precisely, clamp them in position, and tack weld temporary joints to hold the geometry. This alignment consumed roughly 40% of the total welding time. Two plates that should theoretically take 30 minutes to weld end-to-end required 90 minutes when preparation was included. Sorensen noticed that fitters checked alignment by measuring with calipers and comparing against blueprints. If measurements showed misalignment, the fitters loosened clamps, adjusted the plates, remeasured, adjusted again, a process that often required 10 or 15 iterations before tolerances were acceptable. The problem was obvious: the plates themselves. They arrived at the welding station as rough-cut pieces from the shearing department, edges slightly irregular, dimensions varying by fractions of an inch due to cutting imprecision. Those fractional variations accumulated. A quarter-inch deviation on one plate, an eighth inch on another, and suddenly the assembled hull didn't match specifications. Fitters compensated by forcing plates into alignment, using clamps and leverage, and occasionally hammers to bend steel into proper geometry. It worked, but it was slow. Sorensen's insight came in November 1942, while observing fitters struggle with a particularly stubborn hull plate that refused to align with its mating piece. The foreman had authorized 30 minutes for the joint. 2 hours later, the fitters were still adjusting clamps. Sorensen realized the root problem wasn't the alignment process, it was that the plates required alignment at all. If the shearing department could cut plates to exact dimensions, eliminating the fractional variations, the pieces would fit together naturally. No extensive alignment checking, no forced fitting. Drop the plates into position, tack weld, and proceed to final welding. Cut preparation time from 40 minutes to 5. This was not a revolutionary insight. Engineers understood that tighter machining tolerances improved assembly efficiency, but achieving those tolerances required better cutting equipment, which meant capital investment and installation time. The existing shearing machines could hit tolerances of plus or minus 1/8 inch, adequate for automotive body panels, but marginal for armor plate. Upgrading to precision shears capable of 1/32 tolerances would cost approximately $200,000 per machine. The arsenal had 14 shears. Total investment, $2.8 million, 6 months installation time, uncertain return on investment. Sorensen proposed something different. He didn't want to replace the shearing machines, he wanted to add jigs. A jig is a simple device, typically a metal frame or template that guides cutting tools and ensures consistent dimensions. Automotive factories use jigs extensively for drilling holes and cutting curbs, but jigs for straight cuts on a flat plate seemed redundant. The shearing machines had their own measurement guides. Adding external jigs would slow down the cutting process and require operators to perform extra setup steps. Sorensen's supervisor, a production manager named Harold Watson, rejected the proposal immediately when Sorensen mentioned it during a shift break. Watson's reasoning was sound. The shearing department was already the production floor's bottleneck. Shears ran continuously, operators feeding plate into the machines as fast as raw material arrived from the steel mill. Adding jigs meant pausing between cuts to position and clamp the jig, verify alignment, then remove the jig before the next piece. Watson estimated this would add 90 seconds per cut. With roughly 1,200 cuts required per tank, that was 30 extra hours in the shearing department. Total tank production time would increase from 18 days to 19 and a half. The War Department would not approve modifications that slowed output. Sorensen tried to explain that the extra time cutting would be recovered tenfold during welding. Watson didn't want to hear it. He had production quotas to meet, a bonus structure tied to monthly output numbers, and no patience for disruptions proposed by tool and die makers who didn't understand manufacturing economics. The conversation ended with Watson telling Sorensen to focus on his assigned tasks. But Sorensen wouldn't let it go. Over the next 2 weeks, he spent his lunch breaks in the welding section, timing operations with a stopwatch he'd borrowed from the quality control department. He documented that fitters spent an average of 42 minutes per hull preparing plates for welding. He measured plate dimensions directly, recording variations, correlating the degree of misalignment with the time required to correct it. His data showed a clear relationship. Plates with tighter initial tolerances took less time to fit. If shearing precision improved by a factor of 4, fitting time dropped by approximately 85%. The numbers were irrefutable. In early December, Sorensen typed a formal proposal on his lunch break, using a secretary's typewriter with permission after explaining it was for a church newsletter. The proposal was 3 pages: problem statement, proposed solution, and projected time savings. He calculated that adding jigs to the shearing operation would increase cutting time by 32 hours per tank, but would reduce welding preparation time by 140 hours. Net savings 108 hours, reducing total production time from 18 days to 13. He submitted the proposal directly to the plant superintendent, bypassing Watson entirely. This violated protocol and ensured Watson's hostility, but Sorensen understood that middle managers rarely forwarded suggestions that contradicted their own decisions. The superintendent, a former automotive executive named Nicholas Drystat, who had overseen Cadillac's conversion to tank production, read the proposal with interest. Drystat had built his career by listening to shop floor workers, a management philosophy considered unconventional in 1942, but which had produced results at Cadillac. He authorized a test. The test parameters were limited. Sorensen would design jigs for 4 hull plates, the 2 side panels, and the front and rear sections. The jigs would be manufactured by the tool room and installed on 1 shearing machine. A single Sherman hull would be cut using the jigs, then assembled using standard welding procedures. Fitters would time every operation. If time savings matched Sorensen's projections, the jig system would be expanded. If not, the experiment ended. Sorensen designed the jigs in 3 days. They were elegant in their simplicity. Steel frames with precision-machined edges that clamped onto the shearing machine's work surface, creating a fixed guide for plate positioning. An operator would slide plate stock into the jig, which automatically located it at the correct position. The shear would descend, cutting to exact dimensions determined by the jig's geometry. Remove the cut piece, slide in the next plate, repeat. The jigs added 15 seconds per cut, not the 90 seconds Watson had estimated, because Sorensen had designed them for quick release clamping. Manufacturing the jigs took another week. The tool room had to work nights, fabricating components between regular production runs. Cost per jig, approximately $300 in materials and labor. 4 jigs cost $1,200, a trivial expense compared to the $2.8 million required for new shearing machines. On December 18, 1942, the test began. Shearing department operators, briefed on the new procedure, expressed skepticism. The jigs looked flimsy. The quick-release clamps seemed likely to shift during cutting, throwing off the very precision they were supposed to ensure. But the operators followed instructions, cutting plates for a complete hull using the jig-guided process. The plates were delivered to the welding section on December 19th. Fitters received them without being informed they'd been cut using a new method. The standard procedure was to measure each plate, check dimensions against blueprints, and begin the alignment process. The fitters measured the first plate, side panel, specified thickness 2 inches, length 152 inches, width 67 inches. The measurements came back exact to within 1/64th inch. The fitter measured again, suspecting an error. The dimensions were correct. He called over the lead fitter, who measured independently. Still correct. They positioned the side panels on the assembly frame, expecting the usual tedious alignment process. The panels dropped into place. Mounting holes aligned perfectly with the frame's attachment points. The fitters looked at each other, confused. This shouldn't be possible. Plates never arrived in perfect specification. They checked the front and rear sections. Identical precision. The entire hull assembly, which typically required 8 hours of fitting and alignment, was ready for tack welding in 40 minutes. Drystat received the results on December 20th. Total time savings for one tank, 122 hours, slightly better than Sorensen's projection. The implications were immediately obvious. If the jig system were implemented across all shearing operations, and if time savings held constant across all tank components, production time could be reduced from 18 days to approximately 11 days. Monthly output would increase from roughly 90 tanks per facility to 147, a 63% increase with zero increase in raw material consumption or facility size. The numbers seemed too good to be true. Drystat authorized a second test, this time producing 10 complete hulls using jig-cut plates. The results held. Average production time, 11.3 days per tank. Fitters reported that plates required virtually no alignment. Welding quality improved because plates weren't being stressed during forced fitting. Reject rates dropped. The system worked. But Sorensen hadn't finished. While the production trials proceeded, he'd been thinking about the next bottleneck. With hull assembly time reduced by 40%, the limiting factor shifted to turret installation and gun mounting, operations that required precision drilling of mounting holes through thick armor plate. The drilling process was slow because operators had to measure and mark each hole location individually, a procedure that consumed 90 minutes per tank and occasionally resulted in misaligned holes that required re-drilling. Sorensen proposed a drilling jig. Like the shearing jigs, the design was simple. A steel template that bolted onto the tank hull at standardized mounting points, with pre-drilled guide holes that positioned drill bits at exact locations for turret ring bolts, gun mount brackets, and periscope housings. Operators would clamp the jig in place, drill through the guide holes, and remove the jig. No measuring, no marking, no chance of misalignment. Drilling time would drop from 90 minutes to 20. Drystat approved the drilling jig without requiring a test. The tool room fabricated the template in January 1943. First use on a production hull confirmed Sorensen's projections. 22 minutes drilling time, all holes perfectly positioned. With both shearing jigs and drilling jigs implemented, total production time dropped to 8.7 days per tank. But Sorensen still wasn't finished. He'd identified a third bottleneck, electrical system installation. Shermans required approximately 400 feet of wiring connecting generators, batteries, lighting, radio equipment, gun controls, and instruments. Installation proceeded according to detailed wiring diagrams that showed wire routing, connection points, and terminal assignments. Electricians spent hours threading wires through the hull, identifying each wire by color-coded insulation, matching terminals, and testing continuity. The process required 3 days per tank, roughly 1/3 of total production time. Sorensen observed that electricians constantly referred to the wiring diagrams, cross-referencing wire numbers with terminal assignments. They worked slowly and carefully because mistakes were difficult to correct once multiple wires were bundled together. The solution Sorensen proposed was obvious in retrospect, but had never been implemented at scale: pre-assembled wiring harnesses. In automotive manufacturing, wiring harnesses were standard. Instead of installing individual wires, electricians installed complete pre-wired assemblies manufactured at specialized facilities where workers had proper lighting, workbenches, and quality control. A harness could be assembled, tested, and verified in a controlled environment, then delivered to the production line as a single unit, requiring only plug-in connectors. Tank production didn't use harnesses because military specifications required individual wire installation to facilitate field repairs. If a wire failed in combat, crews could splice in replacement segments. Pre-assembled harnesses were considered more difficult to repair because damaged sections couldn't be easily accessed without removing the entire assembly. This reasoning made sense for field maintenance but ignored production efficiency. Sorensen proposed to manufacture harnesses for 90% of the wiring, leaving only the most vulnerable exterior circuits as individual wires. Combat damage rarely affected interior wiring. By pre-assembling the bulk of electrical systems, installation time could be reduced from 3 days to approximately 8 hours. Total production time dropped from 8.7 days to 6.2 days. The proposal required approval from the Ordnance Department, which controlled Sherman design specifications. Drystat forwarded Sorensen's recommendation in February 1943, noting the potential time savings and emphasizing that harness assemblies would be tested more rigorously than individual wire installations, improving reliability. The Ordnance Department initially rejected the modification, citing the field repair concerns. Drystat appealed, providing data showing that electrical failures in combat were almost exclusively radio equipment and lighting, not interior wiring. The appeal succeeded. Harnesses were authorized for interior circuits in March 1943. Implementation required establishing a harness manufacturing facility. Chrysler converted a portion of its Highland Park assembly plant, installing workbenches, wire-cutting equipment, and testing stations. Harness production began in April. By May, the first pre-assembled systems were arriving at the Warren Tank Arsenal. Installation was transformative. Electricians could mount a complete harness in the Sherman hull in 6 hours, connect the plug-in terminals, test the system, and move to the next tank. What had been the single most time-consuming operation in tank production became routine. Total production time dropped to 6.1 days. But the revolutionary impact came from combining all 3 modifications: shearing jigs, drilling jigs, and wiring harnesses. When fully implemented across all operations, these changes compressed the critical path of tank production from hull cutting through final assembly. Combined with minor optimizations to painting, testing, and quality control procedures, Chrysler achieved what every efficiency expert had declared impossible. A Sherman could be completed in 38 hours from the moment raw steel entered the shearing department until the finished tank rolled off the production line. 38 hours, from 18 days to a day and a half. A 90% reduction in production time was accomplished not through revolutionary new technology, not through massive capital investment, but through simple jigs and pre-assembly procedures that cost less than $10,000 per facility to implement. The implications were staggering. Chrysler's Warren arsenal alone increased monthly output from 90 tanks to 387. Ford's River Rouge facility, which adopted Sorensen's methods in June 1943, went from 115 tanks monthly to 422. General Motors' Fisher Body plant, implementing the system in July, increased from 95 to 341. Across 11 major facilities, Sherman production rose from 1,247 tanks per month in February 1943 to 2,134 in August, exceeding War Department requirements for the first time. The increased production came at a critical moment. Operation Husky, the invasion of Sicily, began in July 1943. Allied armored divisions deployed with full equipment allocations for the first time in the Mediterranean theater. Where previous operations had been constrained by tank shortages, Sicily saw American armor in overwhelming numbers. The 2nd Armored Division landed with 232 tanks, the 1st Armored Division with 298. German and Italian forces, fielding approximately 260 tanks total, were outnumbered from the start. The production surge continued through 1944. By January, American factories were delivering 2,800 Shermans monthly. By April, 3,100. The numbers overwhelmed German production capacity. In 1944, Germany manufactured approximately 8,300 tanks and assault guns of all types. America produced 17,565 Shermans alone, plus 2,507 M26 Pershing heavy tanks and thousands of lighter vehicles. The strategic impact went beyond raw numbers. With production time reduced to 38 hours, the interval between design modifications and field deployment collapsed. When combat reports from Normandy identified vulnerabilities in the Sherman's armor, engineers implemented design changes that appeared in production tanks within weeks. Previous production cycles required 3 to 4 months to incorporate modifications. The compressed timeline meant battlefield feedback translated to design improvements almost in real time, creating an iterative refinement process that German industry, working with production times measured in months, couldn't match. Sorensen himself received minimal recognition. He was promoted to senior tool and die maker in March 1943, a salary increase of $18 per week. Drystat recommended him for the Army-Navy E Award for excellence in production, but the award went to facility management, not individual workers. The War Production Board did document his contributions in a technical report distributed to other defense contractors, identifying the JIG system as a best practice for implementation across industries. Boeing adopted similar procedures for B-17 production, reducing assembly time from 42 days to 29. The technique spread through American manufacturing, a quiet revolution that never made headlines but fundamentally altered industrial production capacity. The German response to American production numbers was disbelief followed by desperation. Wehrmacht commanders receiving intelligence reports of American tank deployments rejected the numbers as exaggerated. Mathematics seemed impossible. Germany's entire industrial capacity running at maximum output couldn't match American production from a single state. Michigan's factories alone outproduced the entire Reich. The strategic implication was obvious and terrifying. Germany couldn't win a war of attrition. Every tank destroyed in combat would be replaced by 3 new ones. Every week Germany delayed meant facing larger American armored formations. German attempts to counter production advantages focused on quality. If German tanks were individually superior, each Panther or Tiger could destroy multiple Shermans, offsetting numerical disadvantages. This reasoning was technically correct but strategically irrelevant. A Tiger could reliably destroy a Sherman at 2,000 meters while remaining invulnerable to return fire. But Tigers cost 300,000 man-hours to build. Shermans cost 8,400. For the resources required to build 1 Tiger, America produced 36 Shermans. Even if each Tiger destroyed 20 Shermans before being knocked out, America still held numerical superiority. Combat statistics bore this out. In Normandy, German armored divisions achieved impressive kill ratios in specific engagements. The 12th SS Panzer Division claimed to have destroyed over 200 American tanks during June and July 1944. But American replacements arrived faster than losses accumulated. By August, American armored strength in France exceeded June levels despite months of sustained combat. German armored strength declined steadily, each loss irreplaceable. The psychological impact on German crews was devastating. Panzer commanders understood they were fighting an enemy who could replace losses faster than German factories could manufacture new vehicles. Every engagement carried the knowledge that winning the battle didn't matter if the enemy could afford to lose. American tankers, conversely, knew replacements were abundant. If a Sherman was destroyed, another would arrive within days. This disparity affected tactical decision-making. German commanders husbanded resources, avoiding risks. American commanders accepted losses as inevitable and manageable, pressing attacks aggressively. By early 1945, the production advantage had translated into total operational dominance. American armored divisions in Germany fielded 3 to 4 times as many tanks as equivalent German formations. Breakdowns and combat losses were replaced immediately. German units operating with 30% of authorized strength abandoned damaged vehicles for lack of replacement parts. The industrial war was over. Germany had lost. Charles Sorensen's jigs didn't win the war. The Sherman wasn't the war's best tank, wasn't the most feared by German crews, and didn't represent any significant technological advancement. But Sorensen's methods ensured that Shermans arrived at the front in overwhelming numbers, that every division had full equipment allocations, that losses could be replaced faster than combat could inflict them. Quantity, achieved through simple manufacturing improvements, overwhelmed quality. The post-war analysis by the U.S. Strategic Bombing Survey documented that German tank production was constrained not by raw materials or factory capacity, but by assembly time. German facilities could have doubled output if production efficiency matched American standards. The jigs and pre-assembly procedures that Sorensen pioneered represented manufacturing knowledge Germany never acquired. German industry remained locked into craft production methods, each tank individually fitted and adjusted by skilled workers. American industry had moved to true mass production, where tolerances were built into the manufacturing process rather than corrected during assembly. Sorensen returned to civilian automotive work after the war. He spent 20 years at General Motors' Chevrolet division, eventually retiring as a production supervisor in 1965. He gave occasional interviews about his wartime work, but dismissed the significance, noting that jigs and templates were obvious solutions that any competent tool and die maker would recognize. The fact that they hadn't been implemented earlier reflected institutional resistance to change, not technical difficulty. The tool and die maker was correct. His innovations weren't innovations at all in the technical sense. They were applications of existing knowledge, techniques already proven in automotive manufacturing, adapted to a different production environment. The genius wasn't in inventing new methods, it was in recognizing that existing methods could be applied and having the stubbornness to push the idea through bureaucratic resistance. Management experts studying the case later identified 3 factors that enabled Sorensen's success. First, he had direct production floor experience. He understood the actual work, not the theoretical processes documented in engineering manuals. Second, he documented his proposals with quantitative data. Time savings weren't estimated, they were measured with a stopwatch and verified through controlled tests. Third, he bypassed hostile middle management, taking his proposal directly to senior leadership willing to consider unorthodox approaches. The broader lesson transcended tank production. American industrial output during World War II exceeded all Axis powers combined, a disparity so large that German and Japanese strategic planning became exercises in futility once American production reached full capacity. But that capacity wasn't inevitable. It resulted from thousands of small improvements, procedural optimizations, and manufacturing techniques implemented by workers and supervisors who understood production bottlenecks and possessed the institutional support to address them. Sorensen's jigs represented one improvement among thousands, individually minor, collectively transformative. The cumulative effect was an industrial system that operated at efficiency levels no other nation matched. Germany built beautiful tanks, sophisticated machines with advanced engineering. America built adequate tanks in overwhelming numbers. The war demonstrated which approach was strategically superior. 80 years later, the M4 Sherman remains one of history's most produced tanks. 49,234 units manufactured between 1942 and 1945. More than all German tank production combined. More than Soviet T-34 production during the same period. The numbers represent not just industrial capacity, but the compounding effect of manufacturing efficiency. Each hour saved in production, multiplied across thousands of units, created availability measured in divisions and armies. Charles Sorensen's name appears in a few history books. The decisive battles of World War II, Midway, Stalingrad, Normandy, the Bulge, are remembered. The tool and die maker who made the decisive battles possible by ensuring sufficient equipment arrived at the right time is forgotten. This is historically appropriate. Wars are remembered for combat, not manufacturing, but wars are won in factories before they're fought in fields. The German engineer examining a Sherman captured at Kasserine Pass in February 1943 wrote in his assessment report that the American tank was crude but functional, inferior to German designs but adequate for its purpose. The assessment was technically accurate but strategically worthless. What mattered wasn't the Sherman's specifications. What mattered was that America could build 36 of them for the same resources Germany spent building one Tiger. Sorensen's jigs ensured those 36 tanks could be built in the time required to build two. In December 1942, Building 4 of the Chrysler Tank Arsenal produced one Sherman every 18 days. Skilled workers, proven processes, optimized procedures. The production rate represented industrial best practice, the limit of what efficiency experts believed achievable. By August 1943, Building 4 produced one Sherman every 38 hours. The difference between those two numbers was a tool and die maker with a stopwatch and the institutional willingness to listen when workers proposed counterintuitive solutions. The death ray remained theoretical. The superweapon that would revolutionize warfare stayed on drawing boards. The war was won by a man with a template and a clamp who understood that precision at the beginning of the process eliminated correction at the end. Simple. Obvious, revolutionary. 18 days to 38 hours, a 90% improvement from the civilian who wasn't supposed to know better than the engineers. The engineers were wrong. Sorensen was right, and America built enough tanks to bury the Reich under Detroit steel.